All right. So, guys, continuing our discussion on work managers. So, we saw how to create a work request and how to create a work first, then how to create a work request. And we also talked about, adding some other configurations, some other constraints on these work requests. So, let's now talk about what those constraints are or what the constraints can be. So the idea behind constraints is to avoid to provide additional configuration to the work request such that um, the when the work request is executed, um, it's not too bad on the resources of the device. So you might have seen, say, for example, when the system update happens, right? It requires you to be on Wi-Fi, to be connected to a charger, and so on. So how does that happen? There has to be a way for a developer to specify in the system that I need certain constraints on performing this action. So that's what is at work here. There are these five different types of constraints that the work manager can deal with. First of them is the network type. So, is the network connected or is the network not required? Do you need some connection? That is the first one, first option in network type. Second is network is not required. Third is it's a metered network, which would mean an LTE or a cellular data network basically. The fourth one is unmetered network, that would be Wi-Fi. And finally, a constraint is that you are not roaming, so you don't want to do something when you are roaming. Okay, so these are the type of constraints which related to network that you can specify. With battery, there is a not low. So I want to do this only when battery is not low. I expect it to take a lot of battery power when completing this background task. And if the battery drains and the device restarts because of my background task, it's not a good user experience. So I want to make sure it is run only when the battery is not low. Things like that. Similarly, for charging, it is required that the device is being charged, okay, when I'm servicing this particular request. Similarly, on storage, the storage is not low when I'm doing something. So, it could be, as I said, a bulk download related or a system update download related, which could run in gigabytes, etc. And finally, I want to do this when device is idle. So again, huge download or something that would strain the system. Otherwise, um, you probably don't want to do it when the user is also playing a game and also streaming a video on a parallel activity and things like that. So these are the type of constraints that you can specify. So now let's look at an example of how to do that. Okay, so constraints class has a builder um, which you can create like this, and then you have setters of different types. So set required network type, and then it takes this particular value. Option for this particular value. So as we saw, unmetered, there could be not roaming, and so on. Um, and set requires charging, and then after you add all these constraints, all these setters, you can call build, and then you pass these constraints as a parameter to set constraints on the request builder. So what we see here is a constraint that this job will be run only when the device is connected to Wi-Fi and it is charging. And um, then the question is, what happens if the request was started when you had these constraints? It was I had Wi-Fi and I was charging the device, but in the middle of it, I lost Wi-Fi, or there was a power outage and it's no longer charging. Then what happens? So there is a predefined protocol for handling such situations. Basically, in such an event, um, if the constraint is no longer being met while the work is running in the background, then work manager will stop the work, and it will be uh, retried. So based on the retry protocol, you know, exponential back off or linear, whatever that is, um, it will be retried when all of those constraints are again met. So this particular work is stopped and it's not run until your Wi-Fi and charging is back on. Okay? So there are these checks and balances in place already from the work manager, and you really don't have to worry about it yeah, explicitly. There are some other configurations that you can make besides constraints. Um, First of them is tags. So every every work request that is generated gets a system generated ID, which is UUID, and not really human readable. So what if I want to identify some of my tasks by a human readable string? So that's the tag, and you can. So it's a one-to-many relationship, so a tag can be associated with more than one background jobs. Um, why is that useful? There may be um, certain work requests associated with each other, or somehow groupable logically, and the tag will help us do that. So um, there are method calls on work manager like get work infos by tag. There is also get work infos by ID, for example. But for tag, you can send a string and get a list of all the work infos that are associated with tag. Then you can check status of each one of them and decide an appropriate action. You can also, simply cancel all of them. So, for whatever reason, I don't want to do these tasks anymore. Call cancel all work by tag, and all of those will just go away, right? Um, the other configuration is input data. So you can specify certain data to be passed to the task, and you have this data type, a data class in AndroidX.work. It's essentially a key value pair like bundles. So you can put serializable data on that, and you have set input data and get input data, very similar to get extras on bundles, set extras and get extras on bundles, is what you can use here. Okay. So this data is then passed to that particular task. Um, you can do the get input data in the do work method and then work with the data over there. All right. So next, we have different work states. Um, and there are two different categories for the two different types of works, the one-time request and the periodic request. So the one-time request can go through all these different states. It's created before this point, then it's enqueued, and eventually it is running. That running request can be success, um, and go to succeeded state. So it's completed and goes to the succeeded state. This is one of the end states. It can fail and then it goes to the failed state. So, failure is when, let's say, there is a network loss in the middle of a download request or something like that. Or from the running state, it can be canceled. That is when the developer calls cancel because of certain other reasons, and then it goes to the cancelled state. So all three of them are, final states or end states. The running state job can also go to the retry. Uh, uh, can be sent to retrying on the queue. That is the backoff mechanism that the developer has chosen, and from there it can again go back to the queue and keep trying to get to run from there and so on. By the way, the enqueued request can also be cancelled. It doesn't have to be a running request. So that's another possibility. On the repeating or periodic tasks, you have only one final state. There is no success or failure. Even if it succeeds, it has to be enqueued again because it's repeating. Even if it fails, it has to be enqueued again, because it's supposed to be repeating unperiodic anyways. So this is the state diagram for the repeating requests. There is one more state that we have that doesn't show up here, and it is the blocked state. It's used for chain works, which we'll get to later. Next, we'll talk about how to enqueue the work. We have created a work, we have created a work request. Now we'll talk about how to put it on the queue over here or over here. So enqueuing the work is like this. You create a work request, either a one-time or a periodic work request, as we have seen, and then you grab an instance of the work manager by passing in the context and call enqueue on it. So when you do this, um, the the instance my work is now scheduled for execution based on based on all other things like its configuration and also the state of the system, whether it is connected to Wi-Fi or not, or whatever that is, right? So the okay, so the question is, so this code, enqueuing code will be part of an activity or a fragment. And what happens if device is rotated immediately after this call? So the my work instance was enqueued, and then the activity was recreated. So onCreate was called again, and this line was executed again. Will it put the same work on the queue for the second time? That would mean you'll download the same file, say a huge video file, twice when you need it only once, right? So that's not a good way. So what is the way of avoiding this? The work manager has methods of type enqueue, unique, periodic, or unique, one time, etc. Okay. And what happens here is, instead of simply taking the work request instance, it takes three parameters. So you have similar one for the one-time request also, but it takes three parameters. First one is a string, a unique name that it will use to identify it. And the second one is the protocol to handle when there is a conflict. So conflict resolution. If there is already something on the queue, then what do you do? Here we are saying you keep it, as in you keep the existing one and discard the second instance of the same request. Um, so on the mirror side, there is a replace, which means cancel the one on the queue and replace it entirely with this new instance of my work. The third one is append, which means don't cancel either, but chain the next one, this one, to the existing one. It makes the new instance of my work dependent on the previous one, and we'll talk about chained and dependent tasks in a bit. But basically what it means is, if the existing instance of my work fails or is canceled, then the new instance will not run either. So they are that way tied to each other. The fourth option is append or replace, which is like append, but it does not make the next instance of my work dependent on the previous one. So if the previous one failed or got cancelled for whatever reasons, this one will still be executed. So these are the four possibilities for the second parameter here. And the third parameter is, of course, the instance that you want to put on the queue. You can enqueue something and then you can observe it at different places, just like we saw how to observe the async task progress. There are ways of handling the progress of a work request in your UI or in your hosting code. Okay, so this is how you would do it. We saw get work info by tag. There is also get work info by ID, and then there is a live data variant of both of these: get work info by ID live data, by tag live data, etc. and it takes the appropriate parameter. Here it's ID, there it will be the tag string. And these variants of the methods, they return a live data of a listenable future. So um, listenable future is a Google class which lets you basically observe such components. You can add listeners to them, and then you can observe progress on them. Okay, so that's the main idea here. Okay. All right. So what you're doing here is you're adding an observer. By the way, you'll remember we did something similar in the database app where um, you added an observer to say get all items, which also return a live data of list of items. Okay. So it's a similar mechanism at play. Anyway, so you are adding an observer here, which takes the lifecycle owner, which could be the activity itself, for example. And then the second parameter is a function, which takes the work info as a parameter, thing that is returned. You get the work info and call this method on it. What happens in it? You are checking if the work info state is null. If it's not null, then check if the state is succeeded. And for example, this was a download worker, so you would maybe show a toast that download is complete, or show a notification and move the user towards that particular activity, or to give some indication to the user that it has succeeded and now you want to handle it. Okay, so that's another observer pattern at work, and very useful here. This example shows an observer which is waiting for it to complete, but of course there can be intermediate progress observation as well, and you'll find examples on the online guide. Okay, now coming to chaining work requests. This is a really neat way of basically specifying dependency among work requests. So sometimes you want to first download this file, then that file, etc. Say in downloading and installing an app with dependencies, or certain packages with dependencies, or even upgrading OS, downloading, installing certain parts. So you want to make sure the dependencies are downloaded and installed first, and then only go to downloading, installing the dependent part. So you can achieve that by doing by chaining your work requests. So um, you can specify chaining in parallel or sequential. So certain things don't really depend on each other. They can run parallelly. Certain other things depend on preceding work, so they can be sequential. This mechanism essentially creates a directed acyclic graph, a DAG of work requests, where the children are dependent on the parents. There is no dependence among children, and of course, there are no cycles. That will be crazy. It will just kill it. It won't let it execute properly. Um, Output of the predecessor. So we saw input data. There is output data as well for any request, and the output data of a predecessor is automatically passed to the successor as its input data. And that is also managed by your work manager behind the scenes. Okay, so here is an example. Work manager get instance, blah, blah, blah. Then, there could be configurations, etc. And now we are saying begin with a list where the tasks are plant name 1, plant name 2, and plant name 3. This is an example from the guide again. What this means is all three in this list, they will run in parallel. No specific order, no guarantee of plant name 1 finishing before plant name 2 or the other way. They will run in parallel, but once they are done, then the work request named cache will be run. And once that cache is done, then the work request named upload will be run. So these are sequential, and we are saying .enqueue. So all of these will be enqueued in that fashion and will be executed in that fashion. Okay. Yeah. So work requests specified with begin with list or then list, then can also take a list, not shown in this example, but it can. They are scheduled to run in parallel, as I said. Um, and I also talked about this, so we can probably quickly skip this. So yeah, essential point is cache is dependent on all three of these. Cache cannot start unless plan name 1, plan name 2, plan name 3 are all finished. Okay. All right. Um, yeah. By the way, these are scheduled to run as parallel. Of course, it depends on the system constraints, actual physical system constraints, whether they will be actually run in parallel. But they are, the point is they are not dependent on each other. Now, this is the final part of this. So what happens when um, these different parallel tasks, they create output? Um, if there is no conflict from what you get from task one, parallel task one and parallel task two, of course, that should be straightforward. But what happens if there is a conflict, if both of them create a different copy of the same output? So there is a class called input merger, which handles this in two different ways. First protocol is simply overwrite, which is the default. So whichever task finished later gets to overwrite the output of the previous one. So it attempts to add all the key value pairs, that is the input output data, right? It attempts to add all the keys from all the inputs to the output, but in case of conflict, it overrides the previously set keys. So and this is sort of non-deterministic. You will never know which one will finish, which one of the parallel tasks will finish first or later. You can't really predict that. The second option is array creating, which attempts to merge by creating arrays when necessary. So it won't be just one input. There won't be override. You will get all the options, and then the next task should know how to handle that. Um, this one is not default, so you should call set input merger with array creating input merger class as the parameter when building this type of work requests. Okay, and now a quick graphical example to explain what is happening here. This is the default case, no conflict. So work one produces plant name one elm, work two plant name two tulip, work three plant name three walnut, and there is no conflict. So the output data you get here, which becomes the input of work three, is all of those three key value pairs as they were produced. But what if there is a conflict? And here we assume that work two finished after work one. So work one gave us plant name one elm, which was added to the output. But then work two said plant name one tulip. So it overrode that with tulip. Okay. And plant name three walnut had no conflict. And then finally, the array creating one, it in case of the same key conflict, it doesn't overwrite it. It just creates an array of stuff. So plant name one is a key to a value that is an array, elm and tulip both. Plant name three is also an array, although it has only one value, walnut in this case. Okay. So that's largely about uh, work managers. There are, of course, more advanced cases, which you can look up online through the official development guide or one of the links that I have provided at the beginning of this slide set. The next topic in this discussion is alarm manager, which is what should happen for um, for the uh, for the tasks that have to execute at a given time. We'll discuss that later. Thank you.